Okay, class. This is going to be 3 lessons that I'm going to want you to copy. There are going to be times where you will have to pause. This is lesson 2-4. Use postulates and diagrams. Postulates or axioms. They are rules that are accepted without proof. Name a postulate that you might know. Theorems are rules that are proved. They have to be proven, and these are where we get into our proofs. Now, these are the postulates that you might have known. At least you learned them in Chapter 1. Ruler postulate, segment addition postulate, protractor postulate, angle addition postulate. Okay, on page 98 you will find these postulates. You should turn to that now because you're going to have to write these down in your notes. At any time, please pause. First postulate. Through any 2 points, there exists exactly one line. Remember, we discussed this in Chapter 1. This is how we know that lines are created. Our second postulate. A line contains at least 2 points. Notice it's very similar to the last one. The last one, though, we started with 2 points. Then we got a line. This one, we have a line, and from that line we know there are 2 points at least. If 2 lines intersect, then their intersection is exactly 1 point. We learned that one in Chapter 1 as well. Through any 3 noncollinear points, there exists exactly 1 plane. We also learned that one in Chapter 1. A plane contains at least 3 noncollinear points. If 2 points lie in a plane, then the line containing them lies in the plane. So again, you're starting out with 2 points on a plane, and then a line is drawn on it that also is on the plane. If 2 planes intersect, then their intersection is a line. Okay, so now, here are 2 examples. You have to state the postulate illustrated by the diagram. Notice in the first one, you are starting out with 2 lines intersecting. Then in the second, it says if this, then it is now, the intersection is showing a point. So which postulate is that? If 2 lines intersect, then their intersection is exactly 1 point. Now notice the second one. You're starting out with 2 planes intersecting. Then notice after, the intersection is showing a line. So which postulate is that? Postulate 11. If 2 planes intersect, then their intersection is a line. Now you will not have to memorize these postulates, but you do need to recognize them along with a picture, just like this example shows. Now let's look at this example. They want you to write postulates 9 and 10 based on the picture. That means they want you to use the planes Q, P, the points B, A, and C, and the lines M and N to illustrate postulates 9 and postulates 10. Postulate 9 talks about plane contains at least 3 noncollinear points. So notice on the picture they say, okay, well, we're going to pick plane P. Plane P contains points A, B, and C because those are non-collinear. Let's do postulate 10. Point A and B lie in plane P. So therefore, remember this is the one where you're starting out with points on a plane and there exists a line also on that plane that contains those points. So we chose point A and B. It's lying on plane P. So therefore line N containing A and B also lies in plane P. See, it's passing through the lighter one. That means it's still on the darker one. Remember now, at any time you need to pause to be able to copy these. Okay, I do want you to still continue copying these because these are still great for notes. So let's look at this diagram. Which postulate allows you to say the intersection of plane P and plane Q is a line? And which line is that? Postulate 11. That's the one that talks about the intersection of two planes is exactly a line. And that line is line M. All right, now let's look at postulates 5, 6, and 7. Refer to those and see if you can write down what postulate 5 says using the letters and the planes, what postulate 6 says using the letters and the planes, and postulate 7. Remember to pause. Postulate 5 talks about, remember, the line passes through 2 points, so there exists a line. There exists 2 points on the, there exists a line that contains 2 points. So line N is passing through A and B. So postulate 5 talked about the 2 points containing a line. Now postulate 6 is talking about the line that contains the points. So line N contains A and B. And postulate 7 talked about the 2 lines intersecting at exactly 1 point. So lines M and N intersect at point A. Now this here is where we look at and say, okay, which can't be assumed by the diagram. Okay, well hopefully you notice A, B, and F are collinear. They're all on the same line. We have a line drawn through those points. Notice though the second one, E, B, and D, there is no line drawn through these 3 points, so we cannot assume. So therefore that one is incorrect. Now look at AB perpendicular to plane S. There is a right angle symbol that is right next to that point B. You see it? So it's perpendicular to plane S. It's passing through plane S, but it's perpendicular to it. Now look at CD. Line CD is perpendicular to plane T. No, there's no red box illustrating a right angle, so we cannot assume. AF intersects BC at point B. Yes, that one we can assume. So only the second and the fourth one cannot be assumed. Okay, sketch a diagram to show the line TV intersecting line segment PQ at point W. So that way the two line segments are congruent. So again, remember, take a moment to pause if you need to. So here we go. We're going to draw TV and label points T and V. Now again, you don't have to do mine exactly the same way, but we do want TV intersecting another line segment PQ at point W. So we draw a line TV, put points T and V, then draw a line segment PW, draw point W at the midpoint, mark congruent TW and WV, and then draw PQ. Okay, now this is lesson 2.5, reasons using properties from algebra. Okay, you're going to want to turn to page 106 because you're going to be copying some properties down. Remember again to pause so that way you can copy down these properties. Algebraic properties. The addition property. You do this all the time when you solve algebraically. Now we're going to be using the addition property in proofs. Subtraction property. Multiplication property. And division property. There is one more, that's the distribution property. We don't use that as often, but we also use substitution property, which that one you use when we substitute something in for something else, when we were solving. There's your distribution property. Okay, so now we're going to solve the equation, but we're going to write a reason for each step to the right of it. So this first one is just given to us. Now how would we solve? Well, notice we have the given. Then because I always like to add the variable first or subtract the variable, we had to add 3x to both sides because it was a negative. So our explanation is we add 3x to each side. It's the addition property. Now, how are we going to go from what we have to what we have now, the 7x equals negative 7? Well, we subtracted 9, so it's the subtraction property. And how do we go from that to x equals negative 1? Well, we divided, so it's the division property. Let's do another one. Again, if you need to pause, pause it. Okay, well, the first one is given to us. Now, we like to get rid of the number on the outside of the parentheses, so we distribute. Take 3 times 7 to give us 21, 3 times negative x to give us negative 3x. Now, what are we going to do? We're going to simplify, combine like terms, 14x and negative 3x. So now, that's called substitution. Now you will also see the word simplify, but it's not a property, so you can use simplify, but basically we're substituting 11x in for 14x and negative 3x. Okay, now we're going to add 21 to both sides, or subtract 21 from both sides, so it's the subtraction property. And then how do we get x equals negative 2? We divide, so division. Okay, well sometimes you have to solve formulas for a variable. You did this in algebra. So here we have the formula for a triangle. 1/2 base times height. I want to solve for b. So again, if you need to, pause before you write down, before I give you the answer. Okay, well again, we start out with our given. Then we want to get rid of that denominator, so we multiply both sides by 2. That's the multiplication property. And then I want b by itself, so I divide, division property. Notice we don't show the algebraic work inside. We go directly to the answers every time. That's how we want to write our proofs. Okay, now on page 108 are the properties of equalities. You need to write these down, so please take a moment to pause. Reflexive property. For any real number, a equals a. It's just itself. Here's using segments. AB is equal to AB. Notice it's equal to itself. For angles, measurement angle A is equal to measurement angle A. The next property of equality, symmetric property. For our real numbers, if A equals B, then B equals A. Notice it's very similar to the converse. For segments, if AB equals CD, then CD equals AB. It just flipped. And for angles, if measurement angle A equals measurement angle B, then measurement angle B equals measurement angle A. Transitive property. For our real numbers, if A equals B and B equals C, then A equals C. This one reminds me of the law of syllogism. Here's for segments. If AB equals CD and CD equals EF, then AB equals CD. And for angles, if measurement angle A equals measurement angle B, and measurement angle B equals measurement angle C, then measurement angle A equals measurement angle C. Okay, so now you're going to try to name the properties of equality. So again, if you need to, pause. Okay, now notice the first one. We started out with 6 equals 7, the angles. Now notice what happened to the 7 and the 6. Which property is that? Symmetric. Okay, now look at the next one. If JK equals KL and KL equals 12, then JK equals 12. Notice the first one has JK and KL. The second one has KL and something new, and then it goes from the original to the end. Transitive. Another way to tell transitive is that and it always has 3 statements. Okay, the last one. Notice they both have angle W. Reflexive. Okay, now this is going to be a proof, but we're going to still do it in a diagram form, using the diagram. So we're given AB is equal to CD. We're going to show AC is equal to BD. Remember, please take a moment to copy these. So push pause. Okay, here we go. Well, the first one we marked in the diagram, so AB is equal to CD. So what's our reason? Given. Okay, now we're going to want to get AC in there. So we're going to do, adding the legs adjacent, we're going to do AB plus BC equals AC. And then we're going to do CD plus BC equals BD. Remember that segment addition postulate. Let's do it again. So again, remember that segment addition postulate. Okay, I'm going to have to scroll to the next screen. So now remember, AB is equal to CD. AB is in that statement. AC equals AB plus BC. Notice the second one. CD is also located in that one. And remember, we're trying to get AC equal to BD. Very important. So now we're going to add BC to each side of the AB equals CD. Remember, AB equals CD was our original. So what is that when you add something to both sides? Addition property. Okay, now we want to substitute AC for AB plus BC because remember, AC equaled AB plus BC. And we're also going to substitute BD for BC plus CD because remember, BD equaled BC plus CD. So AC equals BD. And what is that? Substitution. And there we are. We're finished because that's what we needed. Okay, now this is lesson 2.6. This gets more into what we normally look at proofs as. So please make sure you're copying down notes. This one we're going to do a lot more in class, but I do have some proofs I want you to copy. First, what is a proof? A logical argument that shows a statement is true. Now, this you need to know. You need to know what a proof is, just like you need to know what a postulate and a theorem is. What's a two-column proof? There are different ways of writing proofs. We're going to learn them all. This is your first one we're going to learn in this chapter. That's what it looks like. It has statements, and it has reasons that correspond to those statements. So here we go. We're going to write a two-column proof. Please take a moment to copy this before we get started. So, look at the picture. You should always draw the diagram. We're given RT is equal to SU. Now, I did not mark that up, but you should. So RT is equal to SU. And we want to prove the smaller line segment, RS, is equal to the smaller line segment, TU. So let's start out with RT equals SU. Notice we're not given an explanation now. We're just going to give the reason given. Now, we're going to have to introduce, so whenever we want to introduce, we can do the segment addition postulate. So RS plus ST equals RT. Now I've got RS. That's segment addition postulate. Let's do it again for the other side. So what would that be? ST plus TU equals SU. Segment addition postulate. Okay, now we've got RS and TU in our proof. Now we just got to try to get them on the opposite side of an equal sign. Well, we know, remember, RT is equal to SU. So notice we could take those two statements, RS plus ST, to equal the ST plus TU because they're equal to each other. So what is that when we replace? Substitution property. Now, do you notice something that's very much alike in that statement there? ST. So that means we're going to subtract both sides by ST. And the reason why we can do that is because the reflexive property. Now, a lot of times we will skip this one, but we're showing it so that way you know why I did that. Now we can get rid of them and look at to our proof, right? What did we do? We subtracted, and we're finished. Now, I know this is very confusing, And as you're copying these down, don't worry. We will be going through proofs in class. Okay, well, let's look at congruence of segments. I'm going to need you to turn to a page. Thought I wrote it down. Look in your book for congruence of segments. It's the segment congruence is reflexive, symmetric, and transitive. It's in lesson 2.6. First one, reflexive. It's just like the reflexive property of equalities. It's just this one is using congruent symbols. So for AB, it's AB is congruent to AB. Symmetric. This one is if AB is congruent to CD, then CD is congruent to AB. Transitive. If AB is congruent to CD and CD is congruent to EF, then AB is congruent to CD. See? Just like the other ones, but now it's congruence. Okay, let's name a property. CD is congruent to CD. Reflexive. Angle Q is congruent to angle R. Then R is congruent to angle Q. Symmetric. Now, notice this one has the angle in it. If you were looking at your book, you should have copied also the congruence of angles. They're just like the congruence of segments, except for they use the angle congruent mark. Please make sure you have copied those as well, because those are the same, reflexive, symmetric, and transitive. Okay, now what I would like you to do is copy the proofs on page 115 and 116. We're going to go through them in class, but it's much better if you have them already written, so that way you can listen to my explanation. And then we'll do some practicing of proofs. All right. Talk to you later.